Hello, everybody. My name is Dr. David Brumley. I'm a professor at Carnegie Mellon University where I research software security techniques. I'm also CEO at ForAllSecure where we've taken some of those techniques that have shown huge gains and we formed a company with the idea that we want to make the world software a safer place. You can contact me at dbrumley@forallsecure.com. Now, I'm super excited today because I want to talk to you about fuzzing. And I had originally envisioned this to be a multi-lecture series where we really got deep into the weeds. And I showed you how interesting fuzzing research can be. And we got into more advanced topics, for example, like symbolic execution. Now, sometimes life throws you a curveball. In my case, that happened. Earlier this semester, I was diagnosed with a very curable form of cancer, head and neck cancer, actually. And so that put me back. I'm so passionate about this, though, that I didn't want to drop the lecture series altogether. So instead, I've condensed it into one lecture. Now, I have head and neck cancer. I've had surgery there, so if sometimes you hear a funny noise with me swallowing, I apologize. That's just me recovering. Hopefully, it won't detract from getting you excited about fuzzing in research and in practice. Now, at a high level, all the research, all the practice of software security comes down to one fundamental question. How do I automatically check that software is safe? And the reason that we want to do this is even though there's a number of human experts, people like Fluorescence, GeoHot, hacking teams, and if you don't know these people, look them up. They're amazing. But these are really the best of the best. The people who can take any application you give them and find a flaw that allows them to gain access. The reality is the number of people who can find, prove, and ultimately defend against new exploitable bugs is pretty small, which means it's slow, expensive, and manual and unscalable. Now, what we want is we want automated techniques that really keep pace with the speed of software development, but also don't require this huge skill level so that anyone writing software, someone who just learned Python, for example, can really make their software safe so that others don't pay the price for vulnerabilities. Now, I'm going to talk about fuzzing, but I want to put this in context of application security in general. Now, I think of application security really along two different axes. On one axis, you can be looking for unknown vulnerabilities. So you're writing an app and you want to check it for things no one has seen before. And on the other end, you can be looking for known vulnerabilities. Now, if you're in research, you may be like, why are you looking for known vulnerabilities? They're already known, they shouldn't be hard to find. Well, the answer is actually in practice, this is very important. What research has shown is that often software vulnerabilities arise because users use vulnerable library versions. For example, they built an application and they used a vulnerable version of glibc and then their overall app is vulnerable. Or they didn't know how to solve a problem, so they Googled something, they saw some solution, they cut and pasted, but that cut and paste that they just copied into their code base was actually vulnerable as well. And so there's a whole industry around finding known vulnerabilities. Now, the other axis that you can look at is it static or is it dynamic? And fundamentally, these have different theorems if you're looking at from an academic perspective, but they also just have different use cases. So I want to give you the high level bit. If you go back to CS101, you remember, our friend Alan Turing. And you know that some of his contemporaries was a guy named Rice, and Rice has a theorem that says any non-trivial program analysis is undecidable. What that really means is that while Turing showed that the halting problem is undecidable, Rice generalized that and said anything that's non-trivial. So, if it's not just looking for did you indent 4 spaces, but it's actually arguing or trying to reason about the semantics, you're going to have to either have false positives or false negatives. And really what you end up with is on static analysis, you end up with false positives, and dynamic analysis, you end up with false negatives. And you end up with different theorems. Typically, a static analysis soundness theorem is going to be something like, if I say the program is bug-free, it really is bug-free. Now, there's a trivial set analysis, which is you just never say a program is bug-free. You're always correct. But of course, then you have false positives. On the other side, you have dynamic analysis, where the theorem is something like, if I say the program has a bug, it really has a bug. Now, that means you may have false negatives, you may miss bugs. So when you look at this and you look at both the research and the industry breakdown, this has really happened in waves. And the first thing that really took traction in both research as well as practice was static analysis. This is looking at the program source code, and you see a number of companies out there that have been very commercially successful, such as Coverity, Fortify, Checkmarx, and Veracode. Tools that can check software by looking at the code. Now, I said there's this fundamental theorem, and what we see empirically is these static analysis tools have about a 30% false positive rate. What we also know is in practice, tools like Coverity do not match what research is doing as far as static analysis. Coverity is more of a linter, or a checker that's looking really technically at the abstract syntax tree of the program, but it's essentially grepping for bad known programming patterns. But we can think of this in the ideal where it's a static analysis, and the main problem it's going to have is false positives. Now, what we saw rise really in the last 15 years is software composition analysis, which is this problem of finding copies of known vulnerable software. It was really cool for me because I actually saw the rise of this industry. I was writing papers about this 15 years ago, and there are actually tools now that are commercially viable that you can go find. And it's become so important that actually as a professor, one of the things I recommend is if you're doing nothing else, run software composition analysis. At least then you know that your dependencies, your supply chain, you're not just inheriting vulnerabilities already fixed. Now, looking for known vulnerabilities on the dynamic, we see a whole set of tools that are scanners. We see things like Nessus, for example. Nessus will go out and grab a banner of an application. If it's a known vulnerable version, it will tell you. Now, it can't tell you anything other than, hey, I happen to know that's a known vulnerable version. So it's not going to find unknown vulnerabilities. It's checking if you're on the known bad list. Now, the area that's really getting a lot of traction is dynamic analysis. And we're seeing the rise of this in industry. And we're seeing outside of what I'm going to talk about today, we see terms like IASP and RASP and things like that, which I could have gone into if I had the full week, but I won't. Instead, we're going to focus on fuzzing, which is really something that we're seeing take a lot of traction because it solves this problem of how do I automatically check software to make sure it's safe? And it does it in a way comparable to those hackers. It shows you how to break the app, and the longer you run it, the deeper this analysis gets. So fuzzing at a high level is a dynamic analysis that automatically tests your apps for the presence of bugs. So you have an algorithm, the fuzzer, which generates a test, and it runs the app under that test, and based on the result of that test, tells you whether or not the app under that test was okay or not. And it iterates the cycle of testing hundreds, thousands of times a second, scaling at speeds a human could never do. Now, I don't want to downplay the human here. If you go look at George Hotz, a phenomenal hacker, Fluorescence, a phenomenal hacker, they bring something that a fuzzer's never going to bring into the situation. They bring in creativity. But what a fuzzer has is it has the ability to operate at computer speeds and take potentially advantage of parallel resources. So I like to think of this in terms of like chess. A chess game engine can reason about the chessboard 15 moves deep, all different combinations. Humans can't do that. But a human can still bring creativity and still beat the world's best chess computers occasionally. So fuzzing, it's an amazing technique. It helps you test your app, and it's gaining a lot of traction. So as a very simple example, let's think of a program that has a bug in it. Literally, if the program, it takes a user input, and if the input is BUG, the program's going to crash. When I talk about generating a test case, what a fuzzer would be doing is it would be generating a test case like mom, M-O-M, and it'd be running this example code and saying, hey, everything was okay. And then it would iterate and come up with a new input like ba. Run the program again, see it's okay. Come up with a new input like bud. Run the program again, see it's okay, and so on and so forth until it, for example, came up with bug and it saw the program has crashed, and then it would alert the user or the developer that there's a problem. Now, if you look at this, this is kind of cool. I actually created this example on purpose, where if you look at mom, bob, bud, and bug, it's actually getting something called code coverage, meaning that if you take this mom, bob, bud, and bug, and you run it against the program, you can see that all the true-false branches are exercised, meaning that fuzzing can provide a very effective way to test your application overall. So what are 6 reasons that I'm in love with fuzzing, and I think you would be too? Well, the first one is it's industry proven. What we're seeing with the rise of DevOps and the idea of pushing code faster is that major industries are starting to use fuzzing as their primary application security technique. When you look at someone like Google and you think of the Chrome web browser, it's really fuzzing on the back end, which is the main software security technique. When you look at companies like Microsoft, while they still use more traditional techniques like static analysis, what they're seeing is fuzzers are finding a huge number of bugs. In fact, a paper written by a researcher with just one of the fuzzing engines Microsoft uses, and they use multiple, that fuzzing engine was finding a third of all bugs in Microsoft products, and it was the last thing ran, meaning that, all the bugs found by static analysis by the other fuzzers, those were already fixed, and it's finding a third more, so it's extremely effective. We're also seeing fuzzers being used when you have very critical code. And I have here Fastly and Cloudflare's example because they're CDNs, they're content distribution networks, and it's critical. If those apps have a bug, they go down, well, that company just plain stops making money. I also have examples like Motional in here, which is an autonomous car company. And what we're seeing is fuzzing is starting to be used in things like autonomous auto and in aircraft because it helps provide a higher level of assurance than you would get without using fuzzing. And I don't know about you, but when I fly in an airplane, I want to make sure that airplane's safe. So the second reason that I'm in love with fuzzing is we're starting to see it become part of a secure software development lifecycle. Now, this is something I actually didn't pay a lot of attention to when I was in academia, but 3 years in industry, I'm starting to pay a lot more attention. When you go into industry, every company out there is going to come up with a process for developing software, a series of steps, and that's going to be their software development lifecycle. Now, many people do not invent their own software development lifecycle. They use one from the behemoths, with Microsoft being the most popular. And Microsoft says you should perform fuzz testing. And the reason that's in there is because they were getting such good results. So chances are, when you go into industry, if you're not using fuzzing, you're going to get better results by adding it, or you're already going to find it out there. So the third reason I love fuzzing, it's really cutting edge. If you go look at static analysis, static analysis has had 50 years of research. Really, if you think about it, you have 50 years, and to have a new advance is kind of tough. Fuzzing is a much newer field, and because of that, we're seeing more rapid advances. For example, when you look at the Cyber Grand Challenge, DARPA's fully autonomous cybersecurity contest, what it wanted to prove was that autonomous cyber offense and defense was possible, just like it had previously proven that self-driving cars were possible. When it launched this contest, not a single contestant used static analysis to find vulnerabilities. They all used fuzzing or its cousin, symbolic execution. So fourth, it comes down to zero false positives. When you fuzz, you always have that test case that proves the presence of a bug. And the reason this is important is when you look at the software industry, developer time is often the most critical. I mean, if you look at industry, there's something like 0% unemployment in software development right now. And so any time that you can save a developer is good. Now, compare this to static analysis, which often has a false positive in the 30% range. It's a third of the reports a developer wasting time. So that zero false positive is a big thing. It means that fuzzers are actionable. It means that it can, for example, be a reasonable thing to put in your DevOps cycle, where if fuzzing doesn't pass, you block the release because you know that it's a real problem. You have that confidence. Similarly, fuzzing actually can reduce your debug and fix time. So when you go and you look at the research out there, about half of the time is spent fixing bugs or making code that's already written work. So you write a new program and you're going to spend about half your time refining that program so that it works better and fixing bugs. Now, because fuzzing actually gives you a test case, it turns out debugging and fixing it is much faster. Now, I told you that we wanted a world which software is safe. And what I've come to believe is the way we make software safer is that we reduce the vulnerability window. We reduce the time from when a vulnerability is introduced to when it's fixed. And because fuzzing actually gives you a test case, the time to fix it is much shorter because you can use development tools like debuggers, for example, to really inspect and figure out what's going on. And you can use that test case to verify that the problem has gone away. If you want to put this in dollar figures, research out there has shown global software development wages was about $624 billion, with 50% of the time being worked on debugging and fixing code. If you can, the debugging cost is about $312 billion. So about half of the salaries go into this idea of fixing and making code work. The quicker we can make that, the less time, the more developers are actually working on the features that are improving the state of the world and doing cool things. So finally, fuzzing autonomously grows your test suite. As I showed you in that simple example, Fuzzing generated a test suite that got code coverage. It tested every line of code. And that's what we see. The longer you run a fuzzer, it's not just going to find crashes and bugs, but it's going to grow your test suite so that regression testing is more thorough, that you have higher confidence in your code. Because of this, because it's automatically learning as it runs, some even call fuzzing AI. Now we're starting to see fuzzing actually get inside industry standards. We know even without an industry standard, you start to see, hey, we have to have a particular test suite coverage to field your code. A lot of companies do that. They say something like, hey, our standard is 80% code coverage in our test suite. When you go look at things like the FAA and airplanes, they actually have standards about how much test coverage you need. So again, fuzzing provides a way to make this autonomous, to grow that test suite to get the coverage you need without relying on more human effort. So these are 6 reasons I think that you should be super excited to learn more about fuzzing. It's industry proven, it's part of secure software development lifecycle. There's a lot of research on there. If you go look at academic papers and top tier venues, you see papers on fuzzing and how to find deeper bugs or new classes of bugs. You have 0 false positives. It reduces the bug and fix time once you identify a problem, thus shortening the vulnerability window, and it can autonomously grow your test suite.